Hello again, this is Seth and 2 looking at the Dag textbook for Monte Carlo simulation and Markov chain. And today we're going to be looking at the generation of variates from standard distributions. And basically we know that a standard normal distribution we can see has a mean 0 and a variance usually of 1, and this is on support from negative infinity to infinity, so it can have any of those numbers, but they mostly revolve around the mean, which standardly is 0. If we're wanting to calculate the cumulative density function, in this case we will look at our equation and take it, the integral that is, from negative infinity to a point, say z in this case, and if we're simply looking for the PDF, we'll want to look at that with a z-value input where we have the basic equation up here. And just a shorthand notation of that, we can see that x equals a capital N, and then in parentheses we have the mu mean and the sigma squared, which is the variance. And just to generate some of those, we'll generate 10,000 samples here and use it from the right and the left side so that we can see right here that it's revolving around 0 and the tails are spreading out to the left and right quite basically. And next talked about in the textbook is something called the Box-Mueller method. And what this is trying to generate numbers randomly, essentially within a circle. So we're using polar coordinates in a way to generate these, using the sine and cosine for the x1 and x2, and these random generates will be put together so that we can have random numbers made within the standard normal circle. And of course the inputs for these are random numbers which are between 0 and 1, and for an improved method, which we'll look at in just a moment, is to set the x1 and x2 with the natural logarithm of the randomly generated number, the first one, multiplied by -2 and within a square root, and that will give us a nice even distribution, whereas from what we can see right here, when we do just a standard random distribution, we get something that looks somewhat like a plus sign, so it's hanging around along the axes a little bit more than we want. But when we do the adjustment, as I was talking about in the Box-Mueller method, and we multiply it by -2 ln u, then what we'll be getting from that is something more like a circle, which helps us in generating random numbers between that -1 and 1 in this case. And we also have a way of improving our envelope rejection method. So originally what we're trying to do is maximize the probability of acceptance, and as we saw before, we have an exponential function with a lambda and a c, and by changing these we can maximize the probability of acceptance, which will help us to make a distribution that is the best possible. And when we do this improvement of it, where we have lambda equaling the square root of 2, and through some math and methodology we can figure out that c will always be 1/2 of lambda, and in this case the square root of 2 over 2, we have a new probability of acceptance around 88%, which compared to the original way of doing things, which is about 84% rounding up. And we also have a way of generating some log normal distributions, and what we have here is basically we have an x value with what we see the shorthand as I talked about before, the normal distribution with a mean mu and variance sigma squared. And then what we'll be doing is generating y's, which will take these x values that we have and put them as the exponent for an exponential generation of numbers. And in this case, y is always positive, so will never be to the left of the y-axis in this case. And some of the calculations that we have to solve for the mu and the sigma in this case, we can do this mathematically instead of using simulation, and we'll kind of see in just a second in MATLAB how the simulation is very close to the stated formula and kind of revolves around it. And using these equations, we can see that they're very close to the simulations that are being run. And here in MATLAB, we can see that. What we'll be doing is generating, as you can see here, some random numbers that are of the normal distribution with a mean of 0 here. And what that will produce for us is a nice log normal distribution that's curving downwards and eventually approaching 0 toward the end. And that is about it from this portion of the book. Thanks for watching.